Okay, so the topic of today's lecture is digital image forensics, okay? And so we spent a lot of time talking about how images could be manipulated in the last couple lectures. And so, for example, we live in the era of deepfakes, right, where you can't really trust whether the image that you're seeing is actually coming from a real camera or not, right? And in the early days, these were fairly unconvincing. Now it's getting to be a little bit scary that you wonder whether any image that you see can be trusted, right? And so that gives rise to a whole generation of, legal issues, right? How do you know that this image submitted for court evidence was a true image and not a fake image, right? How can you believe what you read in the newspaper and see online? And so that's what this field of image forensics is. And so it's actually not a new thing. So this is a picture from 1864, sorry. The left-hand picture is a so-called photograph of General Ulysses Grant, but it was actually made of 3 separate pieces, right? The background was one piece, the horse and the body was another piece, and the head of the general was a third piece, and these were composited together, right? 150 years ago. So people have already been faking images for a long time. Here's another example of 1939. This is, I think, a meeting with the Queen of England and I think the Prime Minister of Canada, and the man on the right is the Queen's husband, the King. And the King was basically removed from this image and replaced with background texture. So we talked about that last time, right, about inpainting. And so this is pre-digital inpainting. This is an artist, presumably, looking at the photograph, painting over it. And of course, this was all before digital means, right? So we're talking about stuff that happens in dark rooms, probably things where people are manually painting over a big, version of the photograph and then rephotographing it, that kind of thing, right? So all stuff that was before the age of pixels, right? There have been a lot of political reasons why you want to get rid of things, and so there are lots of examples of, people who fell out of political favor being removed from photographs in Russia and China. This is an example from Italy. This is Mussolini on a horse, and then he looks much more noble, holding his sword up when the guy isn't on the right-hand side holding the horse's reins to make sure the horse doesn't go away, right? So you remove the guy, and the image is better politically. Kind of conversely, this is an example that was trying to sink a political candidate, where basically the guy on the right was put into this picture with the guy on the left, who apparently was like the leader of some local communist party. And so then there was this kind of like guilt by association. Hey, these two guys were talking and they look like they're having a good conversation. Maybe you shouldn't trust this guy, right? But that never actually happened. It was pieced together from 2 pieces, right? So, and all this is before the age of digital pictures, right? So it only gets worse as we can manipulate things at a pixel by pixel level. To the point that you might wonder, here are a couple of more modern examples, right? So here's an example from the Deepwater Horizon spill when BP was trying to do a lot of public relations to show that they were doing a great job. And so this was a BP control room where they were trying to show, yes, people are working on stuff all the time. And so the top image was what was circulated. The bottom image was what was actually taken as a photograph. And so what they did was they added some extra stuff on these monitors to make it look like there was stuff going on all the monitors, right? So they basically photoshopped in some stuff on these extra monitors, and of course they were caught, right? And we'll talk about a few other examples as we go through. So I think that it's definitely in the public interest to be able to understand how can we tell whether an image is trustworthy or not. And I'm not sure I have a window open here. So let me just say that all the stuff I'm talking about today, there's one researcher who's really driven the field forward, and his name is Hani Farid. And he used to be at Dartmouth for many years, and now he's at Berkeley. So if you're interested in learning more about the stuff I'm talking about today, which is only just kind of a taste of stuff. So he has a couple of books about, deepfakes and digital image forensics, and he's taught courses on it. And so this is really the guy who knows what it's all about. And so most of what I'm talking about today is taken from one of his books, okay? So let's talk about, some of the main ways that you can tell whether an image is kind of real or not, okay? And so these are going to break down into a few categories. We talked a lot about JPEG images, right? So JPEG is kind of like the standard currency of the web, right? Almost every image that you find online is a JPEG image, right? And images that come out of your camera, generally are JPEG images, right? So that's kind of like, the standard thing. And so it turns out, as we're going to talk about, that there is some clever stuff that you can look at inside the JPEG image file to tell whether things have been corrupted or not. Then there are kind of what I would call camera-related clues that have to do with how did the image actually get acquired on the sensor of the camera, right? It turns out that every camera has kind of a signature that you can kind of go back and infer, was this image taken by this camera, and was it modified after the image was acquired? And then there are kind of, what I would call like kind of, light and physics related things. So independently of, any of the details about how the actual image is stored or created, is what you're seeing in the image physically realistic, right? Things having to do with reflections and shadows and so on, right? So those are the kind of main categories I want to talk about in this quick overview lecture today, okay? So first one is, I guess I would call JPEG issues. We all have JPEG issues. So this is something we talked about in kind of a more image compression context a while ago, right? And so remember, the key idea behind JPEG is you take an image, you divide it into generally 8x8 blocks. So these are usually 8x8 blocks. And then every block, you take the discrete cosine transform, right? That results in a new set of coefficients, right? And then for every one of these coefficient blocks, there is this so-called normalization matrix. This is where the lossy compression happens. This is the quantization part, right? So kind of what happens is that you divide this by a normalization matrix. That results in, and then you quantize the result. So basically, that results in some, approximate coefficients that are no longer exactly what I got originally. And then, once I've got those quantized coefficients, I basically Huffman code the results. And so this was something that we talked about in some detail in a previous lecture about, how does this normalization part work? And we spent a lecture talking about less compression Huffman coding. And so, and when I was talking about JPEG originally, I kind of hand-waved and said, well, standards are complicated. There's actually more under the hood than this in terms of like when you open up a JPEG file, how does it work? So that's actually where all the stuff that you can look at forensics is stored, right? So for example, somehow the image program that's reading the file, your web browser or your Photoshop program, has to know how to interpret this basically binary string, right? And so at the header of the JPEG file, there's a bunch of information, right? That includes how big the image is, so the image resolution, and then it also has to include the normalization matrix that tells us how severely the JPEG image was quantized, right? Because if I don't tell the decoder that, it has no way of knowing how to reconstruct the image, right? So I have to send along the normalization matrix, and I have to send along the Huffman code that was used to do the lossless compression, right? So actually, inside JPEG, there is, a header. So JPEG has a header that includes a bunch of stuff, right? So it includes the image dimensions. It includes basically this quantization table. And to get into it a little bit more precisely, so that's what this normalization matrix is, right? So the quantization table is going to be an 8x8 array of numbers. And then it's times 3 color channels, because I could be coding the, so again, just kind of as a quick note, the JPEG standard uses kind of this luminance chrominance color space. So it doesn't use RGB, it uses Y CBCR, which is kind of like LAB or YUV. So basically, the Y part is the luminance and the CBCR are different color channels. And so the standard allows for each of these channels to be coded with different numbers of bits. And like we talked about, usually the luminance channel is coded with higher fidelity and the color channels are coded with less fidelity, right? So these arrays may be different for each of these channels. And then there's also an extra factor of 2 that comes from the fact that, oh, wait a second. Am I thinking about this the right way? No, this is okay. So total, basically I have 64 numbers, 3 color channels, so I have 192 numbers, right? That kind of specifies how I did the lossy coding. Then I have to also specify the Huffman code. Now, the Huffman code isn't exactly the code itself, and I don't want to get into the details too much, but kind of what it comes down to is what I'm telling the decoder is kind of how many code words of each length there are, right? We know that shorter code words represent more frequent symbols, and so kind of what the header says is, okay, how many code words of length 1 do you have? How many code words of length 2 do you have? And so on. And so basically what it's sending is the number of code words of length 1 through 15 for each of the 3 channels. And also, this is where the factor of 2 that I'm thinking of is. So I don't remember whether I mentioned this in the JPEG lecture, but the idea is that I'm usually Huffman coding the DC value in a different code than I'm using the AC value. Because remember, the DC value is kind of like the average color of the pixel, and so that has a very different distribution than the offset coefficients that come in the AC thing. So basically, when I make a JPEG file, there's a, whoops, I knocked my image here. When I make a JPEG file, there's kind of a different Huffman code for the AC stuff and a different Huffman code for the DC stuff. So basically I have 3 channels, times 2 is 6, times 15 is basically 90, right? So I have 90 numbers here. On top of that, many, not necessarily all JPEGs have actually a little JPEG thumbnail, which is optional. So basically if you look in Windows, for example, there will be a little thumbnail that you see in your directory that it doesn't have to necessarily decode the entire JPEG image to create that thumbnail and put it into the directory. That's something that you can actually snag right out of the JPEG header, right? So you don't have to decode the whole file. This is usually some much lower resolution version of the JPEG image, but this itself, this thumbnail, and this is kind of like the recursive part, is actually also coded in the JPEG standard, which means that it also has its own quantization table and Huffman code thing. So there's another 192 plus 90 more numbers that if this little JPEG thumbnail is in there, it may have different quantization and Huffman coding values for the thumbnail, which seems like a little bit crazy, but okay. So there's this information too. And on top of that, there is what's called this EXIF metadata. And this has to do with, your camera is usually encoding, what camera did you use? What were the, aperture and shutter speed settings? Man, I keep on gesturing and throwing my screen off, which is probably not great for the people watching on YouTube, sorry. All right, this is better. I have to gesture closer to here. So basically, your phone or your camera is going to be putting some extra information into the header file, and could include like GPS location, all this stuff. So whenever I take a picture with my good camera, it has a zillion little camera parameters inside of it that I can use to go back and say, okay, now I understand that this image was underexposed or overexposed because I can go back and see how I took the picture originally, right? And so every camera basically has a different way. There is some standard to this EXIF metadata. Usually there are like 5 pieces that have to be there, and then each piece, so basically there's like 5 subfolders that have to be there, and there's a number of pieces of information inside each subfolder, so some cameras could store a little bit, some cameras could store a lot. Then other cameras can add a whole bunch of extra folders for extra information, and then you have to say how much information is in those folders. So it's not so much what the metadata is, because that can be faked, but it's more like how much metadata there is, how many folders there are and how much stuff is in each folder. And so this kind of corresponds to, 8 numbers, that correspond to kind of how many folders and how much in each folder. So the key idea is that, long story short, if I add up all these numbers, I get, over 500 numbers that kind of characterize what this camera is doing. And the key idea is that these standards, right, for JPEG quantization, for Huffman coding, and so on, right, every manufacturer of a camera can specify its own tables for how it does this stuff, right? It's not like your iPhone and your Android phone have all the exact same numbers, right? Your phone and your camera may have different opinions about whether to store the JPEG thumbnail or not at all, right? Or how much metadata to store. And so the idea is that if I add up all these numbers, I get kind of this fingerprint or this signature. So, so if I add up, or maybe collect is a better way of saying it, I'm not adding them up, all the, all these header numbers, the number that, one number is that you get 576 values that form a signature. And hopefully, every camera has a different signature. And so the idea is that you can take a JPEG file, you can extract all the stuff from the header, and then you can ask, does this match a given camera, right? And it turns out that this signature is actually fairly unique across, thousands and thousands of camera manufacturers, including, all the phones that you have, and it even has a signature that is different according to different programs, right? So for example, when Photoshop saves a JPEG file, it does so with a whole different quantization table and Huffman code and thumbnail strategy than your camera or your phone does, right? So that there's an instant way of telling, okay, did this JPEG file come from a camera or did it come from Photoshop, right? So you can tell whether Photoshop ever touched the image at all. And so in one study, just to see how unique these signatures were, one study of over 9,000 cameras, which included DSLRs, cell phones, and so on, basically 70% had unique signatures. And, almost 90% had, 3 or less in the same bin. Was there a question? No? Oh, okay. Meaning that, it could be that some cameras share all these 576 pieces of information, but, if that happens, only 2 or 3 cameras are sharing this stuff. It's not like you find hundreds of cameras that have the same profile, okay? And critically, each version of Photoshop has a unique signature, right? So that's really important, right? Because you want to know, did this image come out of Photoshop or did it come out of the SD card on my camera, right? That's really important to know. If you had to go back to provide evidence, okay, Your Honor, this is the image I took with my camera, you can, prove that it was originally from the camera and not ever touched by any sort of software, right? And so you can actually, look at the information inside this thing. So I found one place to do this. This may take a minute. So I'm not really sure how reliable this website is because it's cyber.meme.tips. Does that seem like a reliable website to you? We'll see what happens. Not secure, it says. So if I, just to choose a file here, so here's an image that I took on vacation last month, and let's just see. This is the original right out of my camera image. And now I think it's probably got to think about this for a minute. I chose the file, so I think that I have to wait for a minute while it's thinking about extracting the header, because this is actually a fairly large file. And then I guess maybe while I'm doing this, maybe I can open another window. And I have another version of this image that I basically I didn't do anything major in Photoshop. All I did was I used like the auto tone or something like that to make the colors of the image look a little bit better. So let's see how this guy's doing. All right, so this one came out faster. This one looks like it's still thinking. But while I'm over here in the Photoshop version of the image, I can see that, there's some basic info about the image in terms of its size, and then it says image headers 443. You can see there's lots of stuff that doesn't have anything to do with the pixels of the image that's in here. And so here, for example, is like DQT, quantization table. And if I view this in hex, oops, I guess I just have to click on this, view hex. Right, so these hex numbers correspond to the normalization matrix of the JPEG thing. And then there's also, like, if I scroll further down, you can see Huffman table. If I look at that, there's a whole bunch of Huffman code related stuff. So all this stuff is something that Photoshop has decided for me when I save the JPEG image. And if I look at this, it's still thinking, apparently. Well, trust me when I look at the other one, it will be different, right? Meaning that the DQT, the Huffman table, all that stuff would be the same. All this other junk about restart markers and so on would be different. And so, the Photoshop version, even though it was what I would call light Photoshop, it wasn't malicious Photoshop or anything, clearly it's different from my original image. I probably should have used, well, I guess I couldn't resize the image. Oh, here we go. So the original image here has 30,000 image headers, which is probably why it took so long to analyze. And hopefully this doesn't stall too much for me to just be able to see, okay, let's compare, for example, the quantization table for my original image with the quantization table for my Photoshopped image. So here's the hex for one guy, and here's the hex for the other guy, and I can see that these numbers are different, right? So definitely my camera and Photoshop did something different, right? And you could go on from here. I'm not going to dig into this too much, but you get the idea, right? So you could use some sort of JPEG header detective work to tell what was going on, okay? And clearly, one of these has 30,000 numbers, one of them has, 400 numbers. There's a big difference in just the quantity of stuff that is in a Photoshop file versus the raw image file. Okay, so questions or comments about this so far? All right, so here's a cool thing that I learned that I didn't know after reading Dr. Farid's book, which I think is kind of neat. And this is called the JPEG Ghost. Sounds spooky. So this is kind of a clever idea. So how would you, want to alter an image, right? You would probably take an original image and then you would put some new, like for example, in these cases of composites and so on, you'd take a piece of an image from somewhere else and you would put it into the new image and you'd save that as a new JPEG file and you'd pass that off as the original, right? So it turns out that if you're in a situation like this, where you have like an original image, and then somewhere in here, there's an altered piece of the image. So the idea is that I take, I alter one region, and I stick it back into the original. The key idea is that the two pieces are often compressed with different JPEG quality factors. right? And this is a kind of a subtle issue. This is like saying, okay, I am taking your head and I'm putting it on his body, right? The image where your head comes from was compressed with certain JPEG parameters, including like the overall compression ratio, how compressed is the image. And then I'm putting it into a new image that has a whole different set of compression parameters, right? And the idea is that you can reveal these differences in the different regions of the image that were compressed at different rates. And so it turns out that this can be revealed by saving the candidate image, the image that I'm trying to tell is it genuine or not, at different compression levels. So as you approach the quality level of the tampered part, a ghost appears. Let me just illustrate this in MATLAB because it's easier to explain what's going on in MATLAB, okay? So here's the setup. So here is a image of some flowers that I took outside the JEC just recently, okay? And so what I'm going to do is I'm going to save this image at, say, well, let's look at my JPEG Ghost M file here. So what I'm going to do is I'm going to save this image with two different qualities, right? 90 quality and 60 quality. Then I'm going to take a 500 by 500 chunk of the image, and I'm going to replace the middle of the 90% image with the 60% image. And then I'm going to save that as a new 90% image. So the idea is that I'm, suppose I had changed what that flower was doing and I put it in the middle. Visually, all these images should look exactly the same, right? So let's do a just example of this. JPEG Ghost. This is a hard word to spell. Let's wait for this to run. It's doing some saving and some analysis and stuff. Okay. So here's the original image. And let's look for figure 2. Here's the altered image. Now, between the original image and the altered image, I don't think you could tell that the middle pixels look any different, right? Because we're talking about still image quality factors that are still pretty good, right? It's not like I'm taking the middle part of it and I'm crunching it down to like 10% quality. I've got two relatively high qualities of image, right? And so, if you looked at the second image, you wouldn't think that anything had changed at all, right? Now, what I did was I took the altered image and I started to save it with different JPEG compression factors and look at the difference between the original image and the compressed image. Now, when the compression factor is good, then the images look the same, right? Because I saved this originally with 90, so when I compress it with 90, I get no difference between the candidate and the saved. As I start to bring down the compression ratio, suddenly you see this box appearing in the middle that says, hey, the middle pixels of this image are a lot different statistically than the ones on the outside. So you can see this ghost revealing itself, and it's very strong at 60. 60 is the number that I use to put the middle part in, right? So actually, if I'm clever, I can find out that, hey, the middle part of this image was compressed with a different quality factor than the rest of the image, right? And so this is something that, I never thought of this, but it's pretty clever. Of course, as you get further down into really crunching down the JPEG image, of course, you don't get any sort of, statistical relationship. It's only when you're talking about, a slightly visually imperceptible change somewhere in the image. And so you can imagine that if you were taking someone else's head and putting it on someone else's body, that you would see this weird statistical thing happening around that person's head when you reduced it, right? So this would be kind of fun to maybe do as a homework problem next year when I get, when I reorganize the class, right? So Yes, this is the JPEG Ghost. One thing that I should say is that all this stuff will get kind of thrown off if you do some additional processing to the image, right? So for example, I could crop the image, and then suddenly I would no longer be on this 8 by 8 pixel grid that JPEG relies on, right? So one solution of that would be that I could kind of do 64 analyses where I kind of jiggle my candidate image around 64 times in each of the 8 directions vertically and horizontally until I see whether something happens or not, right? So you can kind of get around, cropping type things. And you can certainly get around, you can also find out whether the image has been resaved at different quality factors using a similar idea, right? So the idea would be that I could say, okay, maybe I had a quality factor inside Photoshop, I saved it once. Could I tell whether I saved it again at a different quality factor? Both of those residues are still there. You can kind of see statistically there are some spikes that say, okay, this was saved once at this level and saved once at that level. Okay, so these are kind of like pretty down in the weeds JPEG type stuff, right? You have to kind of know how JPEG works to be able to make any of this inference. And it's fair to say that not every image is a JPEG file either, right? So now what I want to talk about are things that are a little bit more related to the camera itself, the physical sensor, the optics, and so on. And so I would classify these under, I guess, camera-based techniques. So aside from all this JPEG stuff, every camera physically is going to form an image in a unique way. And again, the same idea is at play. Can we tell, based on image formation parameters, whether this image conforms with a given camera's signature, right? And so one kind of clever idea, again, something I never really thought about until I read this stuff last weekend, is that we talked very early on, maybe lecture like 3, about the Bayer pattern, which is a way that most cameras store digital images, right? It's very unusual for a camera to store red, green, and blue individually at every pixel. What happens instead is that the sensor array has a whole bunch of blue sensitive pixels, a whole bunch of red sensitive pixels, a whole bunch of green sensitive pixels, and they're actually usually twice as many green as there are red or blue, because that's where the human visual system is sensitive. And then to make RGB at every pixel, it averages the stuff it doesn't have from neighboring pixels, right? So remember, we talked about saying, okay, I have a Bayer pattern that's kind of like blue, green, green, red, blue, green. And so it's like saying, okay, here I know the red value. If I wanted to interpolate the green and the blue values, one thing I could do is I could say, okay, I could average the greens that I saw at these neighbors to produce the G value, and then I could average the blue values I saw diagonally to get the blue value, right? And so it would be like saying, R is something I keep from the camera. My G is like, 1/4 of the G from the pixel x y plus 1 plus 1/4 G of x minus 1, and so on, right? And the blue would be like 1/4 of the blue of x plus 1, y plus 1, plus ... right? So, non-directly sensed channels are interpolated. And I think we actually had a homework problem on this, or maybe even an exam problem, I don't remember. And this process of going from the Bayer pattern to RGB for every pixel is also sometimes called demosaicing. You may see that word. And again, the key idea here is that your camera is probably doing something smarter than this, right? It's probably not just averaging the 4 nearby pixels. Every camera probably has a proprietary way of deciding how to do this demosaicing, right? It probably is still some sort of a linear filter, right? So each camera has its own way of demosaicing. which is usually probably some type of linear filter. Meaning that you could take this pixel and you put a little filter over that area, and there are some coefficients in that block that tell me, okay, how should I locally average, say, the green values around here to get the green value at my pixel, right? And that process is, again, likely to be unique for every camera. And also, a kind of an interesting thing that I never thought about before is that that means that for almost every image right out of the camera, that the channels are all highly correlated, right? Meaning that the implication is that the, for example, every pixel's red value is ideally correlated with some of its neighbors, right? Because I'm actually creating the red value for 2/3 of the pixels by some sort of local averaging of all the other things, right? Which means that I can predict exactly what's going on in the red channel. It means that there's no independence at every pixel. I'm actually able to synthesize, if I knew my neighbors, I could tell you exactly what I am, right? And that regularity, if that correlation doesn't exist, or it isn't of the form that we expect, we can say that the image has been tampered, okay? Meaning that what I could do is I could, in practice, I don't know what this interpolation filter is for a given camera, but I could figure it out, right? I could take a whole bunch of pictures with my camera, and I could back out, I could estimate what is the interpolation that a camera is using. So the idea would be to, take a few, I'd say many, maybe I should say take some pictures with the camera that I'm trying to tell whether it's this camera or not. And then I can estimate the interpolation filters. And then if a candidate image doesn't have the correlation pattern we expect, then I can say that we tampered with the image. Meaning that, I should be able to tell, I took this image with my, Canon PowerShot camera, right? Well, you can say, hey, look, I know what the interpolation filter is for this camera, and your pixels don't match up with what that camera produces, right? It doesn't match up with the way that the Bayer pattern works, right? So I think that's a pretty slick idea. So certainly, again, this helps me distinguish, not only was I processing the image with software, but also I can narrow it down to, did a particular pattern, is a particular pattern consistent with other patterns that were taken from the same camera, right? And so you can imagine like a photojournalist is supplying like thousands of images from some sort of controversial event, and there's some other image that says, oh yeah, this is from the same guy. You could prove whether or not that was true. So that, again, is kind of like a more software-y kind of approach that has to do, again, with some knowledge about the way physically images are formed on the sensor array. There are a whole bunch of other things that are kind of like this. So one is that on top of this, every CCD array has some noise in it, right? I guess I could call this sensor noise. So it turns out that, we talked before about what are some sources of noise in an image, right? So if this is my sensed image, usually that sensed image is formed by kind of some sort of ideal image, right? So this would be like the noise-free image that would be theoretically formed by the light falling on the positions of the sensor array. In practice, what happens is that there is a multiplicative factor where I don't exactly get this. I get something that is unique to the sensor array itself, right? So basically, this here is this kind of like spatially varying, but it doesn't change for a given camera, but consistent multiplicative factor. Then there's additionally, there's usually some noise, some additive noise that you can't control. But if I took enough images, I could say, okay, I can estimate what is this factor that's going on in every pixel. And again, that could come from just special just specific defects in the CCD array itself, right? Instead of, if intensity of 90 comes onto this pixel, I know that, okay, this pixel is going to actually read 92. It's a little bit high. It's probably not going to be that extreme, but there are going to be these pixel-to-pixel variations on the array that are like the same multiplicative factor every time, right? And so if I have a series of authentic images where I know what the image should be, I can estimate this thing, and this is called, apparently, the photo response non-uniformity noise, or PERNU. So this kind of, you can think about it as multiplicative noise is another kind of camera-based signature. No other camera will have the same PERNU per image pixel, okay? So again, there are some things that you may be a little bit more familiar with in the context of if you're a photographer. There are some other things that are characteristic to a camera, and then we start to get into some more lens type stuff. So there's something called chromatic aberration. I think I have an example of this. So what that means is that when light comes into the lens and hits the CCD array, different wavelengths of light are getting bent differently so that, all the light is not coming to the same pixel exactly. The red stuff is getting bent a little bit differently than the blue stuff is getting bent a little bit differently than the green stuff. And so, for example, if you ever, this is kind of an example of an image I took. I think I took this at the Corning Museum of Glass, which is like a pretty cool place. So you can see here, for example, that there is this fringe that comes from looking through this lens. And even though there's no color on this grid, the blue light and the red light are getting bent differently through the lens, and so you see this aberration, right? Now, great cameras and great lenses have less chromatic aberration, so you're not likely to notice it, right? But, not every camera is so great, and so these properties of how are the different wavelengths of light getting bent through the lens that you selected, again, is kind of like a signature of the camera and the lens, which I think is kind of interesting. You may also be familiar with, lens distortion, right? So lens distortion is something that happens with things like wide-angle lenses, meaning that the way that straight lines appear to be bent outwards or inwards is kind of specific to a given lens. And so the reason I'm talking about these things is that suppose that you were to take a chunk of image and paste it into some other true image, it's going to be very difficult for you to get the chromatic aberration and the lens distortion correct in the piece that you put in, right? So you might say, okay, I'm going to take this image from camera 1, I'm going to do some stuff to it, I'm going to take a piece out of it, I'm going to put that into camera 2's image. All this lens parameter stuff is going to be different for the inserted piece. And so you could really do some detective work and say, hey, look, the distortion parameters of the straight lines in this region are different than those in the rest of the image. Hence, there was some tampering, right? So lens distortion is one thing. And then there's also what's called the principal point. So the principal point is basically the focus around which this distortion occurs. It's something, again, you can estimate. So if you ever use like the MATLAB camera calibration toolbox, you can get this principal point, which is kind of like a intrinsic property of the camera. And so if you take different pieces of image and estimate the principal point, kind of locally, you should be able to say, okay, for an image that's been untampered with, the principal point should basically occur in the same place everywhere. But if you take a piece of the image that has a different, image formation, then you're going to get differing or wrong principal points. Another example is camera skew. I don't know what happened here. So skew kind of has to do with, are the pixels of the image fundamentally square or not, right? And so if you are, for example, recording a TV screen from the side, like you're camcording a movie in a movie theater, then the pixels are not really going to be square. They're going to be kind of like trapezoidal, right? And you can detect this skewness by, kind of looking at a whole bunch of lines in the image that should be parallel and kind of telling, okay, so are these pixels square or not? That will help you determine, are you looking at a cam version of a video, or are you looking at the original theater version of the video? So all these things are related to, intrinsic parameters of the camera. So let me just write these down. I said chromatic aberration, lens distortion, principal point, skew. All of these would be difficult to match for an inserted chunk of image. Okay. So these are all things that I think are, this is almost like optic related stuff, right? Last category of stuff I want to talk about is kind of stuff that is related to light and physics, okay? So here, this is like, the CSI type stuff. Oh, there's a reflection. Is there a reflection right or not, right? So it turns out that people are very bad at judging things that are involving reflections and vanishing points. So for example, let's look at this image here. So which one of these reflections is correct, top or bottom? Let's see a show of hands for top. Show of hands for bottom. All right. So, and a bunch of people undecided, right? So it turns out that the top image is correct from this camera perspective, and the bottom image is not, okay? Now, many of us, myself included, probably wouldn't be able to tell that was true or not. But if you have kind of like, if you think about this from a more mathematical perspective, you can start to do some analysis about, okay, so if I connect the images of a object and their positions and their reflection, all these things have to converge at one particular point. And so you could do some analysis of reflections to say, okay, are these reflections consistent with physical reality or not, right? So in this case, the top part is an image that is correct, because if I connect all these lines, they all converge in the same place. In the bottom image, the tyrannosaur has been moved a little bit with respect to its reflection, and if I draw those lines, I see that they actually have two different convergence points, meaning that the mirror part was tampered with, right? So again, very difficult for a human to eyeball this and tell whether it's happening, but easier for an algorithm to be able to tell. So another example is shadows, right? So here, same kind of principle, if you connect the location on an object with the location on the shadow and you draw those back, they should all converge at the same light source. So in this case, the sun is the light source, and there are these strong shadows of people coming down the walk, and there's one ray, which I guess is this one here from this guy. This guy's shadow is too tall for the physics of the environment, right? It should be shorter, and if I draw the rays, I can verify that there is some stuff in this image that is not physically consistent, right? And again, that's something that a person is very difficult at judging. So here, again, 3 images. I guess these are kind of 3 small images, but you can kind of see the shadows, right? So which of these shadows is okay, and which of these shadows is wrong, right? So only one of these images is incorrect. So image A kind of has some short shadows, image B has some long shadows, image C has some medium shadows. So who thinks that image A is the wrong one? 1, 2. Who thinks image B is the wrong one? No votes. Who thinks image C is the wrong one? 1 vote. So not a lot of certainty. Image C is wrong. The other 2 are okay, right? So again, I couldn't infer this because there's it's very difficult for the human visual system to be able to make a for sure decision, right? But again, this is where forensic science, forensic image analysis would come in to tell, okay, is this image consistent with physical reality? And so here's an example of, you can kind of do the same kind of thing to tell, has an object been inserted into an image? You can think about that by thinking about, are the cast shadows of the objects all consistent with each other? So in this case, this is some forensic thing showing that these ducks in this image are not actually here in this protest, right? And you can tell by going back and analyzing, based on the kind of rim lighting of the objects, here, these cops have, light coming from above, and these ducks have light coming from slightly the side. Or an example like this, some guy wants to seem cool, he's out in the field with these guys in his polo shirt, but, here, the light on him is coming from kind of like the upper right, and the light on the other guys is coming from the top, right? So you can kind of do this forensic analysis to tell, are shadows consistent or not? And there's a very interesting worked example here. So this is a famous photo of Lee Harvey Oswald. And this is a worked example from Dr. Farid's book, as are some of the other examples I've been showing. So as we know, the world is full of conspiracy theorists, right? And so this was a famous example of Harvey Oswald holding a rifle and kind of posing with some, I believe this was like some sort of Marxist propaganda or something like that. And so for many years, this had been debated, is this image real or not? People were saying, oh, it was faked. Look at the shadow of his body against the ground. That looks like the sun is coming from, kind of in front of him. But then there's a shadow of his nose coming from above. And so the shadows aren't consistent, right? This is a fake image. And so then, there was some analysis based on the shadows to understand, could this be consistent, right? So the first thing they did was they built a 3D model of this guy's head based on, I think that they had a mugshot. Oh, hold on a second. No, not this one. This is my image. Let's get back to this. Right, so here's the original image. They had a mugshot that they could use to build a pretty good 3D model of this guy's face. And then this is the 3D model lit from a certain location, showing the shadows look pretty much consistent. And then they did some further 3D modeling of the environment to say, okay, we could make a pretty good guess about where this fence is and how, where this post is and how tall he was and so on. All that stuff was known. And then they cast shadows from a single position of the sun, and they found out that the shadows were in fact consistent with a single light source coming from this one direction, and that this nose shadow was actually perfectly consistent with the ground shadow. And so, again, I'm not sure whether that's going to convince any conspiracy theorists, but there is this kind of analysis that you can do, especially once you start to do better modeling of this thing. And this image is not a real image of Lee Harvey Oswald. This is one of my favorite images from grad school. Okay, so shadows. Let me just write down all the stuff we talked about. The reflections, shadows are a big cue, or let's just say inconsistencies in lighting. And like we said, for both of these, humans are bad at, noticing problems. So that's where you really do need to have some sort of an algorithm that helps you settle these questions a little bit more definitively. And then another thing that is, I'm not even talking about faked video very much, but another thing that you can think about in video is, kind of like, is motion consistent with, physics or gravity, So for example, I know that under the influence of gravity, if I throw a ball, it's going to be a parabola, right? And I can think about how that parabola projects onto the image plane. And so you can look at things like, mass, acceleration, rate of travel, and so on, to be able to diagnose whether or not images and videos are consistent, right? So here's kind of an example of, I don't know why, I guess these images are too long and skinny for me to be able to easily show here. Let's just zoom in here. Right? So when you watch a ball being thrown into a hoop, you can kind of back out, okay, so what was the parabolic motion of this ball, and was the rate at which the ball traveled along the parabola consistent with physics, right? So in this case, there's some analysis that shows that, yes, this is consistent with this guy making the shot, but then you could have some sort of YouTube video where some guy does something different, and you can track the ball, and you can see that, the yellow line is what it should be if it was physics, and the blue dots are what it was in the image. You could say, hey, this was a faked video because something was messed, the ball was inserted later on, and it's hard in something like Photoshop or After Effects to model the whole 3D scene to figure out where everything should be, right? So that's for like YouTube physics debunking, right? Then this is not to say that, we didn't really talk about like all this kind of Photoshop-y kind of detection, right? So definitely, if you're going straight out to, clone regions of an image, like we were talking about last time, this patch-based inpainting, where you were stealing pieces of image to fill in holes, right? So sometimes, even in this day of being able to tell whether something has been faked, people still try to get away with stuff, right? And so I think this was a case where this was a missile launch from Iran many years ago, and they published the top image, but in fact it was fake because it's pretty clear that these two middle rockets are the same rocket that has just been like cut and pasted, and the smoke from one rocket was kind of pasted in from the other rocket. And so basically, it took like a day or less for people to say, look, these pixels are the same. It's like clearly a cloned image, right? And then it turned out the real image was something more like the one at the bottom. And so all this kind of like, if you go down the rabbit hole of like doctored news photos, you can find lots and lots of cases where people are still, even today, trying to get away with stuff. And then I guess this is just a picture on kind of printer forensics having to do with if you see a document, could you tell whether or not half of the document came from some other source based on the way that different printers form different letters, right? So every printer we were talking about has kind of a signature for how it's going to print the letter E. Even if it's the same font, it will have some different rasterization of the pixels. And so you could say, okay, have these two things been spliced together? And so for issues where you're trying to determine the veracity of a printed document, this kind of thing could be issued when you're looking at kind of purely text-based documents. So all this to say that there's a lot of really interesting image processing analysis that you could do, some of which you learned in this class. The last thing I want to talk about is kind of like the modern world of creating totally new images, right? So I don't know if any of you have ever looked at all the stuff produced by generative adversarial networks, or GANs, right? So GAN Breeder is a fun app to play with. So basically, this is a online tool that you can use to generate images that never existed, right? They're images that look realistic, but they're made up of neural network algorithms that kind of learn characteristics of natural images and try to produce things that are kind of interesting looking but not really real, right? So for example, even though this looks like some courtyard somewhere, this courtyard doesn't exist anywhere, and then there are a bunch of similar images that you can create. And so I didn't sign up for an account, so I can't do all this stuff right here, but you can do things like crossbreed, meaning that you can take one image and another image and kind of make children that are interesting looking. So like, for example, I think that you can actually see, I'm not sure if you edit genes, right? So this is made up of a whole bunch of different types of object classes, right, to make this kind of cool looking but weird image, right? And then if you wanted to, I think that the free version, I don't actually get to edit the genes. It will tell me that I can't do it or something. Nope, I have to sign up for an account. I should have made an account, but I didn't. So yes, a friend of mine is super into GAN breeder, and so you know, you can kind of see things that are related. So you can kind of go down this this path of starting from some image that you think is cool and starting to kind of tweak how much of llama and how much of jellyfish is in this image and build these really cool things, and you can save it and tweet it to your friends. So you know, GAN breeder stuff, you know, is usually stuff that looks on the edge of reality, but is clearly not something physically real, right? Like this, you know, dog in the flower is kind of like the crossbreed of a puppy and a flower, but you know this thing doesn't exist in real life. The terrifying thing is that now, oh, so here's some more GAN breeder examples. The terrifying thing is that now you can use the same kind of underlying technology to make images that look very photorealistic that aren't images of real people. So there's a site called This Person Does Not Exist. So if you go to this site, every image that you get is, oh yeah, this person does not exist. Does not exist. So every time you refresh the image, you get a picture of somebody that doesn't actually exist, right? And so all made with GANs. And these images, you know, well, something's going wrong with this guy over here, but you know, most of these images are like perfectly credible looking people, right? Sometimes you'll find, like here again, there's some stuff on the side that doesn't look very good. But, you know, fairly terrifying, right? And, you know, it works with kids and babies and races of all colors and cats and dogs and glasses and beards and all the stuff that, you know, you wonder, like, man, how is this even possible, right? All made from, you know, kind of pieces of understanding what natural human images look like. So again, here, these are some images I saved from before. They're all kind of like, you know, pretty scary. So at this point, you should be like, oh, man, is there any hope, right, for detecting these kinds of images? Luckily, I think there is still some hope for detecting entirely computer-generated images in the sense that the statistics of these images, of computer-generated images, are still different than those of photos, right? And so, you know, these images are clearly really compelling looking, but at the same time, they probably don't have the sensor noise and the chromatic aberration and the, you know, JPEG weirdness and so on that come from real camera images, right? And so you can be assured, at least I think for the immediate future, that if you were to dig into the statistics of these images, like look at the wavelet transform of these images, for example, and start to look at, you know, can you tell the difference between, you know, so you could kind of take it at a meta level, you could train a neural network to discriminate between real photo images and artificial images. I think that you could still do that with a pretty high degree of accuracy, or at least you could tell that these images are computer generated and other ones are not, right? So that's the end of the story. And so I think it's super interesting stuff, right? And now that you have the tools to understand image processing, you too could contribute to this area. And with that, I will stop. So any questions or comments? Let me just shut down my recorder.